Now we are in lesson 3. My name is Engineer Holiday. Hello everyone. We want to talk about purely capacitive circuit. And what is a purely capacitive circuit? A purely capacitive circuit is a circuit that the capacitor is connected directly to the AC. And don't forget, as it's connected directly to the AC source, it can be alternator, it can be AC generator. Just watch lesson 1. Then you would understand that a current must come out from be produced from the source. And if current is produced from the source, it passes through the capacitor of the capacitance, and thereby capacitance C, and thereby creating a charge. The charge that the capacitor will store will now be, let's say, equal to CV. Let's call that one CV. Now the current that is passing through is changing what? Sinusoidally. Don't forget, because it's an AC circuit. So let's say the current is equal to what? The Q over the T. Don't forget that current equal to what? Q over time. That means charge over time. But we write it in this format so that we can also do something there. Now look at the board. There's something I want to show you also. The source have a voltage. The instantaneous voltage of the source, or the voltage supply at every time, is what? V at the point in time is V naught sine WT, where V naught is the maximum voltage, or what we call the peak voltage or amplitude voltage. Now, if current that is flowing through it, that is changing with time, and also as the time is going on, the more the charges are stored by the capacitor. Don't forget, one of the use or major uses or primary use of the capacitor is that it stores charges. So if capacitor can store charge, that means that the charge that will be stored is equal to capacitance of the capacitor times the potential difference. Now let us place this particular charge here. So I'm going to have it as what? CV over the T. That means the CV over the T. Now in place of V, this V is changing with respect to time. Let us also substitute for that. If you substitute it, we are going to have dc V naught sine WT all over what? The T. Now what we are doing now, I want to take derivative of this one with respect to time. If you differentiate this one with respect to time, don't forget, you have to differentiate sine 2t. You have to differentiate 2 first. When you differentiate 2, you are going to have what? 2t, you are going to have 2. Now put 2 there. Then I differentiate sine, you now have what? Cos 2t. So that's what we are going to do here. If you differentiate WT, what do you have? You are going to have what? W attached to what? Multiplied by all this one, CV naught. Then we now differentiate what? Sine. When you differentiate sine, you are going to have cos WT is equals to what? I. Now, having gotten this one, now what do you notice? Look at the current is cos, voltage is sine. Now, if you draw the curve graph, normally, if you draw the sine curve graph or the waveform, now what we notice here that we're going to conclude is cos graph is what? It's like this. Then sine graph is like this. Now if sine graph is like that, this one is for the voltage and this one is for what? The current. For the current. That means you now notice that the current is leading the voltage in this circuit. That means current has started with some that means from here to there is 90. From here to this place is what? 180. So 180 minus 90 is what? 90. That means that the current is leading the voltage by what? Pi over 2. Now, if you can remember, mathematically, cos WT is the same thing as sine WT plus 5 over 2. 5 over 2 is also called 90 degree. What we are trying to say is that sine 60 degree or cos 60 degree is the same thing as what? Sine 150, which is 60 plus 90. So at the end of the day, that means 60 is your WT, 60 is your WT, 90 is pi over 90 degrees is pi over 2. That is to say that the current in quotes, this current I is equals to, can be written as what? CW V naught sine omega t plus what? Pi over 2. That is to say, now if you now compare this equation 1 and equation 2, we can now come out with something and say, in a purely capacitive circuit, current leads what? Voltage by pi over 2 or 90 degrees. That is point number 1. Point number 2 is that now we have gotten our current, we have gotten our voltage. Now we have discovered that current is already ahead of the voltage by pi over 2. And because of this particular thing that has happened here, the power loss in a purely capacitive circuit is 0. Circuit is what? Is 0. So the purely capacitive circuit have a what? I will explain. Now let me put what power equal to what? High V. We all understand that one. What is the current? The current is what? Is what? Let's say the current is I cos WT, because everything here is representing I naught. Everything, because somebody else can say I can replace everything here with I naught. So now sine WT, that means V naught. That means this one now, this V sine WT. So that means the instantaneous power here, it has instantaneous power but it does not have power loss or power expended. So instantaneous power will now be equal to what? I naught V naught sine WT cos WT. Now please don't forget, sine WT cos WT, sine WT cos WT is equals to the same as what? Half sine 2WT. Recall that what? 2 cos theta sine theta is equal to what? Sine 2 theta. If you don't remember, then if you now divide both sides by 2, what we are going to have here, this one cancel this one. We have cos theta sine theta equal to sine theta, then 1 over 2. Sine 2 theta 1 over 2. So that's what I just did here now. So this one is like theta, this one is like theta. So just like sine theta cos theta equal to what? Half sine what? Sine 2 theta. Now, so that's what I just apply here. So this one is like 2 theta, then half. Yeah. So I can clean this part. I just use it to explain that. So what I'm now saying now is that the average power now, or instantaneous power rather, is equal to I naught V naught over 2 sine 2WT. So that is what? The instantaneous power in a capacitive circuit. Now, also, let us now equate this one, this current now, because this I equals to, if you remember the formula from the one, which is from lesson 1, I instantaneous, this is instantaneous current, this is instantaneous voltage, this is what we have here, instantaneous current, is equals to what? I naught sine omega t. That is the formula. But because we are having this now here, so we compare, when we do comparison in wave, you still write the same thing. WT plus what? Pi over 2. So that is what we are comparing this one with this one. If you compare now, bring this one out, the position of maximum current, bring it out and equate the two of them. What do you have? You are going to have CWV naught equal to what? I naught. Therefore, if you divide both sides by what? Let us make sure, don't forget, V equal to what? I R in Ohm's law. So if V equal to I R, let us ensure that our resistance is equal to what? V over what? I from Ohm's law now. So let's bring this I naught here, and let's bring CW here. So if you do that, what do we have? We have CWV naught equal to I naught. If we want to take this one away from here, divide both sides by I naught. Sorry, this one cannot cancel this one. So this one will now be what? CWV naught over I naught equal to 1. Now let us take CW away from there. I want to have what? Divide both sides by CW. CW. What do you have? This one will cancel this one. So what we have left is now be what? V naught over I naught equals to what? I over. What is W equal to angular velocity, which is what? 2 pi f. Don't forget. So we can write it as what? WC or CW or equal to 1 over 2 pi FC. Now this one is what we call the inductance, the resistance, capacitive in what? Reactance. Reactance across the capacitor. That's what we call this one. This X is what we call a reactance. Why would we call reactance? Because their resistor does not what is not large enough to cause a power loss in an AC. So in that was they only react. That's why we call it what? The reactance. They are smaller resistance, very minute, that their effect does not cause a what? Does not expend power from the AC. It does not take too much from the AC. So in that case, now what we are saying now is that, look at it, V naught what? Over I naught, which is equal to R, we check. But our R here is not normal R, but X is the symbol we always use. XC, that means what? Capacitive reactance equal to V naught over I naught equal to 1 over WC. W is equal to what? 2 pi FC. Now recall that V naught over I naught is the same thing as what? VRMS over IRMS. Don't forget to, if you don't know it now. V naught over I naught is proportional to what? Is the same as what? VRMS over IRMS. Why? If this one now, this VRMS, it has a formula of what? V naught over root 2. So if you divide V naught over root 2, divide by I naught over root 2, that means V naught divide by 2, divide by I naught divide by 2, root 2 rather. If you remove the proportionality now, I mean the division, you are going to have V naught over root 2 times, then the root 2 will go up, root 2 over I naught. At the end of the day, this one will cancel out. You have the same thing as what? V naught over I naught. So therefore, this one can be taken as, you can write it as VRMS over IRMS. So take note of this formula. You can circle it. Very, very important formula. So now we are able to explain things on the board, but let me summarize everything for those of you writing WAEC, those of you writing JAM, or those of you in 100 level. Now, number one is that a purely capacitive circuit has its current leading the voltage by pi over 2. We have seen it on the board here, or 90 degrees. In other words, we can say the voltage is lagging the current by pi over 2. That means current leads, but voltage lag. Number two, the power loss in a purely capacitive circuit is 0. Why? Because all the parameters are changing. Check. Would the reason be that this one will be changing? That means this time will be changing. Angle, where is it? Okay. The angle, if you check the formula for power loss is what? I RMS VRMS cos phi. That's what I gave you in our last in the lesson 2. Now all the parameters here are changing, no constant value, and because they are changing, therefore it will lead to what? Power loss not what to be 0 in the purely capacitor. And one of the major reasons is that the current and the voltage are not in phase. are not in phase. In this case, one lead the other. So in that case, it's possible, it's very difficult for us to have a power loss in such a circuit. Number 3. Now, in a capacitive circuit, they store what they call electrical energy. I didn't state it on the board. So electrical energy is being stored in this kind of circuit, because when they store charges, the charges will not be used for electrical purposes. Number 4. Now, in this circuit, the reactance across the capacitor of capacitance is 1/2 pi Fc, where C is measured in farad. Don't forget, C is capacitance of the capacitor. C is the capacitance of the capacitor. So in that case, when we talk about C now, C is measured in farad. And when you plot the graph, Xc against frequency, if you check what is the relationship between frequency and capacitor, frequency and Xc. Xc is inversely proportional to what? Xc is equal to 1/2 pi Fc. So that means Xc is inversely proportional to what? F. So the graph will be like this. Here's how the graph will look like. We plot the graph of reactance across the capacitance against frequency. So that is inverse graph. So it depends. Not like the lassitude that the resistance does not depend on frequency. Please take note of that, because we are going to combine them under RLC circuit. Now, I think that is a major thing. Then the last one, according to Ohm's law, which is the last one, is a V equal to IR. But in this case, we are going to use IC, I mean XC. I equal to what? XC, which is voltage across the capacitor. Voltage across the capacitor here is equal to what? The current that will be supplied times the reactance across the capacitor. So with this understanding, I don't think you should have problem with this capacitive circuit. I hope I hope you enjoy yourself. My name is Engineer Halide. Thank you very much for watching our video. Thank you. God bless you.